Yo, my people, welcome to this video about a vulnerability that I discovered in the USB stack Linux kernels. Honestly, this here is a lot of information, but I'm gonna try to share all of this information in just one video. So please pay attention. I'm gonna mention a lot of open source tools in order if you want to find vulnerabilities in the Linux kernel, this video is for you. If you love Linux kernel, this video is for you. If you are entry level in the Linux kernel hacking, this video is for you. I'm gonna show the timeline because I discovered this vulnerability by accident when I was doing fuzzing in cars, in the infotainment system, the USB-C port of the cars, and in a travel in a conference. So that is quite a bit interesting. I discovered this not in this country that I am living right now. I discovered in another country. So this CVE is crazy because also it's quite a bit interesting because I discovered this vulnerability, and there is another entity. Who knows what the hell is that entity that discovered the same vulnerability through LLMs, but I discovered this by accident and without AI. And another entity, of course, they discovered in a massive web using LLMs. So just to be honest, this vulnerability is a kernel half memory leak. It's not like too interesting, but of course I create this video because for me there is a lot of information that I learn and I love doing this. And I was working trying to find vulnerabilities in the USB stack from February from 2026, right? And all right, so let's start, guys. There is a lot of information. So first of all, we're going to check the USB stack, the parts in a very fast way, the Syzkaller also in a very fast way, because honestly it's necessary one entire video about Syzkaller, one entire video about Raw-Gadget, one entire video about USB fuzzing in cars, and when. So I'm gonna just pass like very fast, but of course you're gonna understand not in deep level, but you're gonna understand in overview, you know. So I'm gonna put the vulnerability timeline, debugging, analysis, conclusion. Just a disclaimer, I'm working in PCA cybersecurity in Budapest, and I was trying to find a vulnerability in a car doing this process, but I don't find the vulnerability in the car, and I found the vulnerability in my free time doing another stuff. So yeah, all of this that's just just a disclaimer. So yeah, let's start about, of course, the USB stack. And before show the USB stack, we need to understand the system call. Just a fast overview. The system calls are the functions that receive the calls from the user space. When you are running a program, of course the program have functions, and these functions could go, for example, through the library libc, and the libc functions call to the Syscalls, and the Syscall interface are into the kernel. So this is with kernel privilege, with the root privilege, right? So for example, let's put an example very fast. You create a program that it is within a C language that it is printf. So the printf call the corresponding live function in libc, and the libc call the system call write. Right, and write is basically the traduction on printf when you are gonna print something through the screen. So very fast, let me show you what I'm talking about. If I put Syscalls, this is the Syscalls. The Syscalls is the fundamental interface between the application, I mean the user space, and the Linux kernel. And here we have a list of the Syscalls. And for example, this is to map memory in the heap, and the write that I was talking about is, for example, this, correct? And you can check, for example, also the libc function of write. If I am not wrong, is this is the parameters of this function. For example, the size count, the file descriptor, the buffer, and you know. Alright, so the question is how you communicate with the Syzcall when you are trying to find vulnerabilities. We are gonna check this, of course. But before, let's talk about the USB stack 3 layers. The first layer communicates with the user space. For example, if you connect a keyboard, if you connect a pen drive, all of these devices have a specific drivers. For example, when you connect a pen drive, this is the driver of the mass storage driver, remember. And this is in the layer 3, okay? And this communicate with the user space in order to save data in the pen drive and so on. This is a driver. For example, you connect another driver with, for example, a keyboard. This is another kind of driver. If you connect the mouse, this is another driver in this layer is enabled. But of course, the brain is here, the USB core. This is the layer that manages everything, because, for example, the host controller is the layer. This is maybe is very obviously, but of course, just let me explain it because this is very useful in the next slides. The host controller communicate with the hardware. So, for example, if I connect a USB-C, a pen drive, for example, this one, whatever, this host controller starts past the communication that is in the brain, in the core, and say, hey, for example, the USB core say, hey, who are you? For example, and the USB device need to say, I am a pen drive, I am a keyboard, these are my descriptions, my characteristics, my features, and all of these communication needs memory. All of this communication needs, of course, code that in order to communicate with the hardware, and so this is the host controller that communicate with the hardware in order to all the functionalities of the USB core could work properly. But this is just like a bridge of communication within the USB core, and also they use the host controller could allocate kernel memory in the heap, in the kernel heap, in order to work with all of this. Also, this works with rings. Honestly, if you are gonna check the kernel code they use back, of course, it's like a lot of lines of code, and this is like a very summary way. So, when you connect, say, hey, this is the pen drive and this is the USB stack in the device, in the mobile, cell phone, or the laptop, and so on. You say, hey, who are you? I am a keyboard. I am a camera. I am a mouse. Okay, send me your keys, your HID report description. All right. Okay. And after that, the USB core configure it and choose the specific USB driver. For example, in this case, HID. For example, this will be for the keyboard. This driver is enabled if you connect a pen drive, the USB driver of the mass storage. This is in the layer 3 that communicate with the user space, right? And after that, the device can communicate, as you can see. But what is this information that exchange in the first phase when you connect the device? This is very interesting and this is very useful. For example, this is the USB device. Let's say that this is a hub, for example, that have a lot of configuration, and each configuration have an interface. The interface is a functionality. And for example, let's say that the functionality is a keyboard, or a mass storage, or a network card, or a camera, audio input, a video input, and there are many infinite USB devices. So this is the interface, and into the interface you have endpoints, right? So the endpoints are a bridge or data pipes in or out for the descriptions. Okay. So the endpoint is the place where the descriptions, where the information between the USB device and the USB core in the laptop or in the embedded device communicate. Okay. So endpoints belong to interfaces. So, but there is by default one endpoint that establish the first stage communication, that is the endpoint 0, and this allow to the device. But the other endpoints this below to one interface. So one interface, one functionality will have many endpoints, as you can see. And configuration description. Right now I have connected my mouse, I have connected another USB devices, and you can put, for example, LS USB, and you are going to check all the USB devices that you have connected. But what happens, you put LS USB in verbose mode. Alright, you are gonna recover what I am talking about here. For example, the BID, this is the vendor ID, this is the product ID, this is one specific for each device, right? The vendor ID, the product ID, this is specific for one device. For example, if you connect the Raspberry Pi, the vendor ID will be of the Raspberry Pi, and so you know. So here the vendor ID in this case is this ID, and the ID product is this. After that starts the descriptor configurations, and after that is we have the interface, and the interface of course is the functionality, and each interface has an endpoint, and here we have the endpoint. So this is about the bytes per interval, a lot of information about the endpoints, endpoint address, and so on, right? Here we have another example. I'm gonna show you another example that is different. For example, this one, this interface, right? This interface descriptor, we have here more than one interface. We have one interface, another interface, in total 3 interfaces, and each interface has its endpoints, you know, their endpoints. Okay, so this is like in a very fast way. So right now let's talk about the Syzkaller. If you're gonna try to find vulnerabilities in the Linux, of course one of the most intelligent ways is to do fusing to the Linux kernel. So how does work this fusing? Okay, the Sys manager is the core. This is open source, of course. You can download, run in a local way, and in 1 hour, or maybe in 30 minutes, you can set up this, power on, and after that you are doing fusing to the Linux kernel. Of course, this process is not too easy because you need to download the Linux kernel, put it in a virtual machine, and run and connect to SSH, and I'm gonna explain this very fast. So here we have, for example, my host. In my host, I have the Sys manager that have connections with a database, right? That recover the code, the kernel code coverage. I'm gonna talk about this in the next slides. But the name of this is corpus. Okay, so this is when, of course, you are gonna find vulnerabilities in the Linux kernel. You need to compile the Linux kernel and put this in a virtual machine. In the best cases, in a virtual machine. For example, in the best cases, QEMU is a node. So these blue rectangles are the virtual machines, and you communicate from the host to the virtual machine through SSH. Okay, and into the virtual machine you put this binary. The binary is sys executor. This sys executor receive the code of the fusing and do the Syscalls. Basically, the sys executor is the program, the binary that do the Syscalls in the kernel, and after that we are gonna check the logs, the dmessage logs, with Kazan, with a kernel address sanitizer or kernel code enabled, and we are gonna recover. For example, if we manage to find a crash, of course this is interesting for a crash, and we check the crash in the dmessage logs of the virtual machine. Of course, this information is very useful for us. So this crash happened in one part of the kernel code. So this kernel code is called coverage info. So the fusing in an intelligent way get this code, this kernel code, right? Recover this kernel code and put this to the database. So basically, you from at the beginning of the fusing, your database is absolutely empty. But after you generate a crash, of course, you know that this crash happened in this line of the code, and right now after that you are not gonna do fusing more like from zero. You are gonna do fusing from this kernel code, more functions through this. So basically, if you get a function in the kernel code, you are gonna do more fusing. Pay attention to this function that you already generate a crash in order to go in deep. For example, the functions that call this function. You got it? This is kernel coverage. And the way that communicate to the Syscalls is using something called Syzcall descriptions. This is a language. It's not a program language. It's just a way to describe Syscalls. Because let me explain you here very fast. This is Syzcall descriptions. Basically, for example, the Syzcall open. You can put here the parameters, and you can control here, you can mutate here the parameters. So when you are gonna call a Syscall, you are not gonna call with static values, you are gonna call with variables that could be random. For example, the file descriptor will be another one. For example, the buffer will be another value in order that you want to generate a crash. So you define this in a Syzcall description language that the name is Syzlang. Let's say Syzlang, yeah. Syzlang. So for example, if you write in Google about Syzlang or Syzcall description, you are going to find this. So yeah, Syzkaller uses the declarative description of Syzcall to generate, mutate, minimize, serialize, and deserialize program sequence of Syzcall. So basically, you control the parameters of the function of the Syzcalls. And that is a very intelligent way in order to do fusing, because of course you have the control of the parameters. If you can control the parameters of the Syzcall, you can manipulate the inputs and so on. Right? This is a very fast way, but if this already exists, sometimes you don't need to create, because this is already a here. When you download, you already have. Let's check if we can find this. Okay, but in this repo are these kind of Syscalls. So there are two options. One, that if there is like a new kernel driver, you need to write this from zero, the Syzcall descriptions that touch your driver, right? Because the goal is, of course, do the Syzcall that touch the driver. In this case, use the Syzcall that touch the USB core. Okay, you got it. I think so. So in order to do that, the Linux kernel is like a big word, but in this big word there is just one driver, one stack that is totally different to the rest one of the another. For example, how do you inject USB packets in this research process of fusing? For example, of course we are gonna try to communicate with the kernel with the USB functionality, but how will you create this from user space? Because remember, the communication happen between the host controller that is in the layer 0 that communicate with the hardware. So the communication starts when you connect a pen drive, when you connect a USB device. You cannot do this by default from user space. So the question is how you are gonna do fusing to the USB stack if the communication is from outside, start from outside. So let's put an example here. For example, when Syzkaller is doing fusing in the network devices, because of course in order to, for example, create TCP packets, you can create TCP packets from user space, and you can inject net packets to the kernel from user space. That's absolutely possible, for example, through the feature to on top. But what happens with the USB? You can create USB message, USB descriptors from user space. And let's talk about that. That will be the setup that we should do. We need to something from the kernel emulates some device, and this device create the USB message, right? So in order to do this, there is a driver called Gadget FS that allow you to emulate in the user space a USB devices, as you can see here. All right, so here is the Gadget F that allow you to emulate a USB device, and after that you can communicate into the same machine through a USB device that it is emulated in USB in the computer, in this case, or in a virtual machine. But wait, the problem with Gadget FS is that you cannot change the message of the USB descriptors in this protocol, in this phase of communication. They say, hey, who am I am keyboard, and I have these are my descriptions, characters, and so on. You cannot change this. You can emulate, but it's very limited, the features, the change that you can do. So in order to do that, we will create this open source. All of this is open source. It's Raw-Gadget. It's a driver that is absolutely the same than Gadget FS, this one here, but this allow you to change whatever you want, put arbitrary message, arbitrary content at all. So this is USB Raw-Gadget. This is the comparison with Gadget FS, and here we have the GitHub. The process to install is very easy. In the most of the cases, you need to install this in a Raspberry Pi, because I'm gonna show you the setup, but this driver allow you to emulate and create arbitrary messages. So yeah, that will be the case, right? For example, this we could implement in a Raspberry Pi. And why in a Raspberry Pi? Because the Raspberry Pi has already this DWC2 driver that has the functionality that allow you to emulate a USB device. And if you install this in a Raw-Gadget, basically you have a portable Raspberry Pi that you can connect in a physical way to the laptop, and after that you can emulate a device wherever you want through the Raw-Gadget that is in the Raspberry Pi. So this is the setup, guys. This is the Raspberry Pi Zero, right, with the Raw-Gadget. Through one USB-C micro port you power on the Raspberry Pi, and through another port basically you emulate the USB device. You send the USB messages here through the USB device, right? Through the USB through this port, through the USB micro. So this is the images that we are looking in this slide. You emulate through a Raspberry Pi USB device. You connect this, for example, let's connect this in this laptop. Boom, and after that the laptop will parse this like a USB device, and after that you can do fusing right now with this. So this is one feature, right? And yeah, the interface here is stable because the sysexecproc is the binary that execute these Syscall language descriptions. These communicate with Raw-Gadget, and Raw-Gadget basically communicate and do all the magic here, and you can do fusing. So let's put here more clear one more time that you can do here, do the calls of the Syscalls of the USB core, and you can do fusing even just in a virtual machine, right? All right. So this is the test with the Raspberry Pi. For example, this is just a test. In this case, this is the Linux host, and I am behind this. Cheers, it is a Raspberry Pi 5, and I connect through SSH to the Raspberry Pi, and I put play and the emulation of the Sys program basically. And here I am, for example, emulating that I am a keyboard, and in this moment appears the letters that I was writing through the Raspberry Pi here. So here I am emulating a keyboard. I was just doing this, testing the setup, and it works. So you can use Raspberry Pi 5, 4, whatever, but the recommended is use a Raspberry Pi 0, because in the normal Raspberry Pi you need to manage with the how to power on. And if you power on with the USB, basically you are not going to have another USB-C port empty. And using the Raspberry Pi 0, you have two USB-C micro ports. One is for power on and the other is for communication. So Raspberry Pi 0 is perfect. There is no more to see. This is perfect for this Fuzzing. Okay. All right. After I create this Fuzzing setup, I tested this in cars, in my job. So this is an infotainment system or a head unit, you know, the computer that allow you to put the radio and so on, the games, the music, and in the most of the cases you have a USB-C port. I think in all the infotainment systems right now we have a USB-C port. So what I did, I emulate this with the Raspberry Pi, and I download this code. I think that I didn't show you yet the Syzbot. Let me explain you very fast what is the Syzbot. So the Syzbot is this one here. Okay, Syzbot. So the Syzkaller is running in a cloud on live 24/7 from maybe 6 years ago, and is trying to do Fuzzing all the time. All the time is trying to find vulnerability bugs. So the Syzbot was able to find like thousands of bugs in the Linux kernel. So you can just visit here, and if you are more curious, for example, if you put C to upstream USB, you're gonna have the vulnerabilities that was found or bugs in the USB. And if you put here subsystems, and here you have a lot of drivers and of components of the Linux kernel. In this case, let's put the USB. Here are the vulnerabilities that were discovered or reported in the last days. For example, this was reported 6 hours ago or 11 hours ago, 1 day ago. Let's talk about, for example, the Kazan slab on breeze. Here you have the message logs of this vulnerability. And it's interesting because you can recover what the exploit or the code that generate this. In order to do that, you have two options. One is to check the Syzlang. Remember the Syzlang is this one, for example. This is Syzlang. Here you have the Syscalls with the specific parameters that generate this specific bug, this specific memory bug. I know there is memory because it's detected through Kazan. Kazan is a feature in the Linux kernel about kernel address sanitizer. If you install a Linux kernel with Kazan, if you compile your Linux kernel with Kazan, you are able to check when something happening in the memory, when a vulnerability appears in the memory, when the memory is crashed or whatever happening in the memory, you are gonna see with Kazan, because by default through the message log we cannot do this. So in order to see this through the message log, we need to compile our Linux kernel with Kazan, and after that we are gonna find all of these vulnerabilities. And the C code of this, for example, is this. So this C, if you compile and you run in your computer, in your Linux, maybe you are gonna find this bug. You are gonna get this crash report. So okay, you can do replay of this. All right, so that's what I was doing. I download through Python script around 3,000 Syscall bugs or vulnerabilities related to USB. I download absolutely all the USB-C bugs related to vulnerabilities related to USB-C, and I put in my Raspberry Pi Zero, and I was doing a replay of this, and also I was trying to mutate. And there is like a lot of setups. I think I'm gonna upload the video of this in another video, because of course it's a lot of information. So yeah, I connect the Raspberry Pi Zero through the USB-C port, and after that I was waiting in order to wait if there is like a crash or not, if this exists a crash or not. This is interesting because I showed this in B-Size Budapest, and remember that of course we don't know what is the operating system of the hard unit, and this is intended for Linux USB stacks. And as you can see here, of course, is not a Linux USB operating system. This, honestly, wait, it is a real-time operating system, but of course I was trying just for fun, just for curious, okay, just for fun, just for curious. So of course I tested in infotainment system of cars that were Linux, okay, and yeah, this is an Alfa Romeo Giulietta, very old car. This car is 2013, and the operating system is, I'm not going to talk about the operating system, but I'll just with a like example of this. So I was doing this in not many cars, just maybe 4 cars, and in January 2026 I was doing this in a car, and this is like a test bench in my job, and I was doing fusing the IBI USB stack of a vehicle in my job. So but I didn't get the results at all. I just get some warning messages and so on. I know that this is like LTS kernel, because if you are gonna find here what is like LTS kernel Linux, is Linux long-term LTS kernel. Is a specific version of Linux kernel archives that receive critical security patches and important bug fixes for extended period. But of course, in the embedded devices, the Linux kernels are patched. Well patched, it depends also the build date. I'm gonna upload the video about that because it's a lot of information, but yes, on 14 March 2020 I traveled to Hack GDL, is a security conference in Guadalajara, Mexico. I was invited for these amazing guys that invited me, and I was doing fusing the IBF of a Toyota Corolla 2023, and with the same setup, doing replay. Remember, in this moment I was not doing like a fusing, I was doing just replay all the USB, because I was doing a research. Of course, if we have in the Syscall, if we have in the Syzbot all the vulnerabilities related to USB. Here, for example, I can do replay. If I download all of these that, for example, that are the one that are open, maybe there is like a probability to crash the IBR of the system. But it just in a short period of time, and using one attempt, I was able, and I replay, of course, not all the vulnerabilities, because this will take a lot of time, because you know, and when you connect the USB device to the car, this emulates and the device, and after that you need to emulate the disconnection, and after that you need to connect again and disconnect again and connect. But of course, this is, I'm talking about the emulation. In a manual way, you just need to connect the Raspberry Pi Zero, and after that, boop, and you wait. But each back requires at least, it's not too fast. Is like maybe each back takes around maybe 3 seconds, around this quantity of time. Yeah, but what I did is like, okay, I was doing something, and I come back to the hotel, and I discovered a bug in my hotel room by accident. Because what I'm doing, guys, I was doing fusing replay all the USB bugs to my laptop, and I was with the kernel 6, so one of the last kernel in that moment, 6.18, 6. something, right? So I mean, like, through these ports I connect to the laptop to get the 5 volts, and through this port also I connect to the laptop in order to do fusing, because I was just doing tests. and you were doing tests. And after that, boom, something happened very crazy. So basically, I was doing this replay in my laptop in the Linux kernel 6 or something, and something happened. So this was the setup I was doing in the Toyota Corolla. Is quite a bit complicated because I connect this through the IBI and the 5 volts. I connect the 5 volts to my laptop, and I connect to the Raspberry Pi Zero through the SSH, because the Raspberry Pi Zero is connected through Wi-Fi to this router, and I connect to this, the same WLAN, and I connect through SSH to this, and from this I run the Fuzzing, or I run the replay of this box. And yeah, this is the Syzkaller in progress. As you can see in the left, is I am running this box. And in this conference on March 14, 2026, someone saw. I already showed what I discovered in my laptop. And someone say, "Hey, bro," because I say, "Hey, guys, I think I discovered a zero day." And I just show it the video. I didn't show it like in deep the code. I just showed the video that my laptop was able to be crashed doing this kind of process. And on March 14, 2026, someone get up his hand and say, "Hey, bro, I was wondering if you could try this in my laptop." And say, "Yeah, sure, why not?" And another after that appears and say the same. Appears his hand and say, "Hey, bro, I would like to test this in my laptop as well." So I say yes. Remember, I was with the LATAM car hacking village in Mexico, and I was doing this. I just discovered this like one day before March. I discovered this on March 13, and I showed this. I put this in these slides that I already showed in that conference, because the title of the talk was how to do USB Linux kernel Fuzzing, right? So this is Syzkaller in reproducible model targeting Linux kernel 6.16.10. So this is the laptop of my friend with the Linux kernel 6.17.10. And these are the kernel logs on a computer Linux kernel 6.17 while the bug trigger was executed. And after the crash, the system powered it off automatically. Okay, so if you don't mind, let's put a video. And I think I need to find another. Alright, let's put. Alright, so in this moment the Raspberry Pi is connected, doing the replay. This is the Raspberry Pi doing the replay, and this is the message logs in the left, and the right is the Linux kernel version, as you can see. And basically I was reproducing the crash. What I get in my laptop in the hotel room of the conference, I was doing in the laptop of my friends that I meet in that moment.
Claro, entonces está apareciendo warning como que está ejecutando, donde de repente verías el kernel panic o
exacto, ¿no? Exacto. Ok, exacto, total.
Ya, y veo que hicieron el name and sub para ver, bueno, el CR, para ver la versión de kernel que se está utilizando. Ya, ¿creció? ¿Sí?
Yeah.
¿Creció? ¿Sí?
And not only was crashed, bro.
No, está bueno. Como 7, como 5. Bien, loco.
Awesome. Congrats.
Tu CVE, encapsularlo y reportarlo.
Tengo que reportarlo.
This is a video in the same moment in another perspective. I was very fucking happy. Look at my slide, jeez. Look at this reaction. Come on. Yeah, so my name is Daniela, you know, aka reverse everything. Yeah, so after that, okay, I come back to Budapest and I say, okay, let's go to do the bug. Honestly, I didn't have enough time because this is not like an interesting vulnerability because it's just like a crash at the denial of service. But of course, so what I did is like I reboot the kernel with command lick enable and boot in that kernel. Alright, so my suspicions in the first place was that this was like there is like a memory that it is not deleted by the kernel. This was my assumption in that moment because maybe the data not removed by the kernel, so accumulation of memory and trash, you know. So yeah, so in order to do that is a lot of complicated because you need to download the Linux kernel of the version that you want to analyze. For example, here I download this, and after that you need to build, to compile with the feature kernel memory leak. As you can see here, I enable this in the config file, and after that you build. Just wait. It takes a lot of time, maybe more than 1 hour. In my case, it takes like 40 minutes or even more. And after that, boom, I get the compiled kernel with command leak of the version I was trying to do. In this case, the Linux kernel 6.12.38, because this also was vulnerable. And yeah, because yeah, this feature allows you to see memory leaks in the kernel in a specific path. I'm gonna talk about that. All right. So after that, I install this in my laptop, and after that, when you power on, you can decide if you can go to your default Linux kernel or you can go to the compiled Linux kernel. So what I'm talking about that is this. I installed this with these commands. Command leak debug. So yeah, you know, in the grab process, in the boot process, you pick up this, and after that, boom, you are into the Linux kernel with the command leak. You need to mount the command leak in the path syskernel debug with this command sudo mount debug as known syskernel debug. And after that, you can check the logs that are in the kernel in the user space, right? As you can see here, you can use your echo scan sudo t blah blah blah, and you here discover, for example, here is like unreferenced object that it was not deleted, something like that, and you can verify that commonly was mounted correctly with this command. Yeah, honestly guys, I think that I need to show a video of this setup because it was a bit complicated. So you need to block the HID from the Raspberry Pi because what happening, and maybe if you recreate this, you are going to happen the same. You need to block the HID from the Raspberry Pi. What I mean, the HID is the human interface device that if you don't block, basically in the moment that you are going to do fusing, you are going to emulate the keyboard without pressing you manually. Because the fusing, the replays of the bugs have this HID bugs, and of course you don't want this kind of bugs that close power on through HID, like literally emulating a keyboard. You need to block this. So and after that, you need to connect through SSH through the machine, through the machine. So what I was doing, to the laptop that I was doing the testing, I enabled the SSH and I connect the laptop through SSH in order to do this process. So in the laptop was connected the Raspberry Pi Zero, and also I was connected to this laptop through SSH, and I was managing the Raspberry Pi through SSH and the laptop through SSH. So through two different SSH connections. Please don't confuse this. I think, let me check if I have a video that I could show you guys, because honestly, alright, I get a video guys. Alright, we have the video here. So this is the setup. So in the left is the laptop with the kernel compiled with command leak. In the left is the laptop connected to the Raspberry Pi Zero. and in the right is the attacker machine that is connected to the laptop through SSH. Here we have 4 terminals. One terminal is the dmessage log, the other terminal is looking for the command leak outputs, and in the computer we are running the Syzkaller replay of the bugs of the Syzkaller. As you can see, the Raspberry Pi is there. So yeah, this was the setup. And yeah, in the terminal 1, just dmessage log. Terminal 2 is about the dmessage log, but with a lot of filters to check this specific HCI, because I was thinking that this is emulating that many times I connect, disconnect, connect, disconnect, connect, disconnect. So I was thinking, of course, this is something related to the HCI, the host controller layer in the USB stack. That's just I put here some filters. In the terminal 3 is basically just to check the command leak output, right? And in the terminal 4, I was just checking the mem info, the prop mem info, the info used, because of course, if a crash happened, it means like the kernel heap is using a lot of memory until there is a time that there is no more memory in the heap of the kernel to be used for another process that it is doing the emulation with their USB device, the Raspberry Pi, sorry. Alright, so here is what I'm talking about. In the terminal 1, dmessage log, terminal 2, dmessage log with the filters. Terminal 4, we have here the kernel mem leak output. So here we have, as you can see, guys, unreferenced object in this size, unreferenced object. And when I mention unreferenced object, I'm talking about, of course, about objects that was not deleted in the heap in this case, because I already put this kind of filter for the command leak. Terminal 3 is the memory consumption, the memory available, right? And here is what I was running in the Raspberry Pi. So this is a loop that recreate the CVE-2026-43432, 2026-43432, and this is basically is a replay of a specific Sysbox and put this in a while true, because these Sysbots of course emulate a USB device that is connected, and also emulate this connection, and also emulate the connection many times. What happens if you repeat this like for 1 hour, for 30 minutes, for many times? Of course, a lot of things will happen, guys, believe me. So yeah, this is happened many times. This is the output in this case of the command leak. As you can see, let's check this. 1 new suspect memory leak, 1 new suspected memory leak, 5 new suspected memory leaks, 5 new suspected memory leaks, and so on. So here we have the cat image like log command leak, you know. And yeah, so what I verified with this debug process that I repeat at least 3 times is that, of course, in this kind of process appears this memory leaks. And if you go in deep, you're gonna check the logs of in what part of the code happened these memory leaks. Let's check this analysis. Oh yes, this code is very deep. So when it comes to the denial of service, all right. So the cause of the denial of service is let me check the okay, we are correct. It's like a static analysis of the kernel code identified a memory leak vulnerability in the Linux kernel HCI host controller interface USB subsystem, specifically in the XSCI disable slot function. The bugs occurs because the XHCI allow command allocates both structures, the command structures, and when I mention command is the command that comes from the from the device, or even from the USB core, right? And this is saved in the heap, but also is saved another structure called completion object. That is, of course, associated with the command, if it is completion or not. But in certain error paths, the code incorrectly calls free. That is, of course, very safe, because if you free the memory of command, of course, that's correct. But what happened? You don't delete the memory of the completion object, right? That's the problem, because in this case here you are just deleting the command structure. You are not deleting the completion object. With this function xci free command, you are deleting both the completion object and command instruction. So basically, when this function is running, a kernel memory leak happening. So as a result, the completion object is never released, as I mentioned, causing a kernel memory leak, while a single occurrence as negligible impact an attacker capable of repeatedly triggering these error paths, for example, by continuously attaching, detaching, or fusing malformed USB devices, can cause the lag to accumulate over time, potentially leading to memory pressure, degraded system stability, or denial of server conditions. The vulnerability does not provide direct primitives for code execution, of course, or privilege creation or memory creation. It's just a resource exhaustion issue. Remember, that's the reason I already told you in the beginning of the video that this is a denial of service vulnerability. It's like a resource exhaustion issue caused by improper dynamically heap allocated XCI command resource during error handling. So yeah, XCI free def. Doing short, your device is gone. Tell hardware to release a slot and 10 free driver memory. This function is very similar to XHCI disable slot, but this function is working on other Linux kernels versions. So let's explain the vulnerability with the code, of course. All right. Kernel leak. Setup. Disable the slot. Honestly, I need to put here disable a slot. Yeah, that's what I'm talking about. Okay, so as you can see, this is the function that when you remove the USB device, this function is called. When everything is correct, you are gonna call the function. What function? This function here. All right. Free command, and this delete the command object and the completion object. But what happened if this condition happening here? Something's happen with the, so for example, if the host controller is dead, what happened if the host controller is disabled? We don't need to disable the slot if the host controller is there. So in that moment, you are gonna just free the memory of the command. But in this case, of course, you are not deleting the completion. So in that moment, when the host controller is dead, you are gonna just delete the command. And that's the reason that's here is the vulnerability. So the solution of the vulnerability basically is to copy this line here. And with this, you are gonna avoid this resource consumption of the kernel heap, right? And here is like a basic graphic. So XCI disable the slot, allocate the memory, and when HCI allocate command is executed, there are two objects allocated: the completion structure and the command that is the main object. And the main object is a structure, and one part of the structure is the completion structure. But if you just delete this, of course it will be in the like a leak in the heap, And if one error condition occurs, for example, when the host controller is halted or is died or something happened with the host controller, boom, you are just gonna free the command, and basically this is still allocated. Okay, so just very fast, what is the HCI? Is like very similar to the other USB controller interfaces. HCI uses device slot wherever the device is connected. You connect a USB device, and there is like allocation of the slots. We are talking here slots in the last version of Linux. Everything is managed like a slot. So this is allocated as slot, enable the slot, assume the address, create internal data structure, tears down when the device disconnects. So Linux asks the HCI to perform operations to enable the slot, address configure, and so on and so on. Okay, and this kind of process, there is like a memory called transfer request blocks, because the USB core requests something to the HCI through a ring. So this is a ring. The USB core put here the request, and the HCI controller take the request. And after that, also events. The USB core puts, the HCI controller put here events, and it means like the responses, and the USB core pick up here the response. So this is in the heap, right? So here you can put the commands and so on. So to finish this, on June 2026, I realized another entity from the same bug. Because remember, I sent the vulnerability report on the same month. I'm talking about on June. So on June 2026, I realized another entity from the same bug with AI. The CVE was published in May. I realized on June that a few weeks ago on May, the vulnerability was published. They don't have the proof of concept. This was a considered 100%. And remember, I uploaded my YouTube video on March. And I published the 0 day of this vulnerability on March, but without technical details, you know. So I sent what I discovered after the bug and so on the same month. But everything happened in this day because I was writing the vulnerability description with the proof of consent and so on, with the Syzkaller bugs, with the code and so on, with the wild true program that I uploaded to the Raspberry Pi Zero. And honestly, guys, this is a coincidence 100%. So and the observer behavior appears considered when the very recently identified CVE-2026-43432, published on May 8th, whose root case matches the behavior I reproduced during testing in my assessment. Because the official description on the CVE indicates a similar attack vector. It's like a local attack capable of repeatedly attaching the attacher or fusing USB devices may amplify the memory leak. This is exactly what I was doing from January, trying to find vulnerabilities in my job with this, and I found a vulnerability in the official Linux kernel in the laptop. That's crazy. Therefore, the same vulnerability that was manually identified during my research and in these car hacking village, travelers and so on March 14, 2026 was assigned as CVE approximately 2 months later in May 2026. So, yeah, honestly, I think that I could help because I could support the CVSS score, because if you are gonna check this here, the vulnerability, for example, Sentinel-1 or here, there is no CVS based score, because of course this was like a vulnerability found by AI. When someone report something with AI, of course there is no manual analysis that you support the CVS score, you support the proof of concept. And of course I can do that. Maybe if I have time I can upload the proof of concept, the video proof. That would be awesome, guys. So as you can see, there is no CVS score here, and this is the vulnerability that. And this is the affection. If you want to see if your Linux kernel is affected, this art version from 4.down to this one, from 5.down to this one, from 5.down to this one. And here, what I am talking about is this. The flaw sees in the HCI disables load function with the USB host controller system. When the error handling plug executes, the code cascades free directly on a common structure called blah blah blah. This is associated with the completion structure that was outside the common structure. And Repeated triggering the error path, of course, causes the kernel memory leaked. But there is something root case attack vector, yeah. A local attacker capable of repeatedly attaching the attacker and fusing USB may amplify the leak. The vulnerability does not probe correction or privilege escalation. So, honestly, guys, this is very difficult to generate because, first of all, the host controller needs to be in one state, and in order to find the state is very difficult. At the moment, I don't know how to find this state because I have a Syzbox that I replayed, and some of these generate this, and also it not just depends of the bugs that you replace. It depends also the current state of the heap, the kernel heap, because sometimes you are using your laptop in another sound, and of course the Linux kernel heap is using that. So it depends of a lot of factors, guys. So believe me, is not something that you play the proper constant and replay. It depends on a lot, but if of course it exists, yeah, I get a code that generate this. So yeah, the Linux kernel commit that introduced this vulnerability, disable xload, was from 2016 in the version 4.13. This is the Linux kernel commit that introduced this feature of the XCI disable slot. Right now the Linux kernel, of course, is like more than 25 million online. Of course, it's absolutely crazy. Yeah, so what I mean, and in the in the car that I was analyzing in the first phase, was with version 4.4.36. Doesn't really matter the version. It could be any version, but I checked it in the kernel code of this embedded device, and of course I realized that this function is not present. So it means like in the Linux kernel 4.4.26 that was previous to the 4.13 in 2017, this function code was not present. So that's the reason that because when I found this, I checked it in the card that I was trying, and I checked the version. I recovered the kernel image, and after that I checked it, and it's not vulnerable because of course the function is not present. So why is not present? Because in the moment the function that replaced HCI disable slot is using the free dep. It's not vulnerable to the memory leak because yeah, it handles in another way, and this function is absolutely very secure. All right. Here I mentioned this. I checked, of course, that this function is not present in the kernel code 4.4.3x, so that's the reason I verified in the original embedded device firmware, and also I verified in the open source Linux kernel code. That is, you can check in the Elixir cross references. It's the Linux kernel code. These are the affected versions that affect this vulnerability, guys. You need to update if you want. You don't update, doesn't really matter because it's just a denial of service that is quite complicated because someone needs to connect, and after that just crash. Is very similar to someone that power on. Maybe I don't know. Maybe for another person is very interesting this, but who knows? Okay, so I checked another kernel, the 4.19. Of course, is after the 4.13 when the vulnerable function was introduced in the Linux kernel, and I checked it, and yeah, this is vulnerable, guys. For example, if you check this, if you are doing embedded device research and you get the Linux kernel version of your embedded device, and you check that your embedded device have this vulnerable function, of course your embedded device is vulnerable to this, and you can replicate. You have a USB-C port, you can put replace book and replicate what I showed today. So yeah, here we don't have we have here the vulnerable function because of course this is just calling the kernel free command. Okay, so the patch for the vulnerability is present in Linux kernel from the Linux kernel version 6.19.40. So if you have a version that it is previous from 4.something to this, is you need to check if this is vulnerable on your embedded device, and you need to update. So yeah, the update basically is up in this line to change the kernel free command with this kernel with this xhci free command The fix for the vulnerability was to properly release fault behavior allocating credits, the common instructor and his associated completion instructor by calling HCI free command. No vulnerable kernels. For example, this is not vulnerable kernel because right now, of course, it's already patched. Official patch for the vulnerability. This is the patch. You need to check the patch. Sometimes right now, if you are using AI, just checking the commits of the patch, maybe you are going to find another vulnerability. So that's the reason I put here the patch, just like in order to wait that if you will need to go more in the you need to find more vulnerabilities in the Linux kernel. Sometimes the patch are already vulnerable to another stack. So yeah, this is the commit with the patch, guys. Vulnerable devices I have in my home. I have one Kali that is here. It's this one here that is vulnerable to this. So I can do the proof of concept here in this and have another laptop with the same vulnerability. And conclusions: remote command executions through the Linux USB style in head units. Okay, let's be honestly, regarding the potential impact of the US stack, recent IBI related remote command execution cases have been associated with proprietary USB drivers of vendor stacks. For example, this one, CVE-2026-43432, writing than the upstream Linux USB stack. Why? Because the Linux USB stack is very well tested, very well fixed, and in the most of the cases, you find vulnerabilities that are related to denial of service. This is what I found because I was trying to find a vulnerability from zero. And I was trying to find, of course, like a memory corruption, something interesting with my Fuzzing, and I was spending a lot of time, and I just found a denial of service. But yeah, given the majority, the extensive Fuzzing or hardening of the mainline Linux USB subsystem, achieving remote command execution tree is considered highly unlikely, but not impossible, guys. Honestly, not impossible. I think it's a matter of time. I think everything is matter of time, believe me, but it's quite a bit complicated, but not impossible. So in the most realistic scenarios, the impact will be limited to the denial of service condition or system instability requiring to restart. Higher impact scenarios are more plausible only in head units using proprietary or heavily modified USB stacks. Alright, so yeah, the vulnerability is just that denial of service is difficult to trigger in the real life. Sometimes it is possible to trigger, sometimes not. Sometimes we don't know what ahead with the kernel heap memory, because of course you need to debug like a crazy, but of course if you have time, go for it. Not interesting vulnerability, it's like more a bug, but anyway, just interesting to learn about the Linux kernel and learn a lot about the USB stack. And of course I presented this in another Latin American conference in Spanish and also in the B-Sides Budapest about how to do USB Fuzzing, and I think I'm going to upload a video about more in depth how to set up USB Syzkaller, because of course it requires another video. So thank you very much, guys. I really appreciate your time and see you in the next one. I hope you learn. Please check about the Syzkaller, the Raw-Gadget, put that shit in the Raspberry Pi Zero and go for it. Find vulnerabilities in the USB Linux card, replicate, reproduce, bugs, understand the code, and so on. So see you soon, guys.